Hello, hello, hello. Ooh, we have a live Gianna and a live Sarah. And not that and hello, Gianna. And you guys can feel, I love losing in the competition to hello speed. I love losing in that competition. So thank you for the hellos. And you're welcome to use your voice for the hellos. It's like, and then you could turn off your, turn off your mic again. You can, but okay. So hello, Gianna. Hello, Osmael. Hello. Oh, wait, okay, I'm going to do it visually first. Wait, oh, people are coming. So hello, Gianna. Hello, Sarah. Hello, Montserrat. Hello, Stephen. Hello, Abdel. Hello, Kay. Hello, Ash. Alejandro. People still coming in. Okay. And now the chat. Hello, Gianna. Good afternoon, Osmael. Good afternoon. And hello, Jada. Ooh, a double. Hi, Montserrat. Hi, Sumaya. Hi, Brianna. Did I say? Oh, I never noticed Gianna and Brianna. How did I not notice? Okay, I'm gonna keep going. That's like stupid, but not. Hey, Ashley. Good afternoon, Stephen. Good afternoon, Alejandro. Awesome, awesome. Okay, who else did I not say? I think that's did I say Brian? Okay. So hello, hello. Okay, we're gonna continue to make tracks here. Oh, good afternoon, Jose. Sorry. Good afternoon. Awesome. Awesome. Okay. We are. Okay. So now today, oh, no, there's someone else. Oh, and at top of the afternoon, Abdel. I love the top of the afternoon. Okay. Here, the top of the hour. Oh, and someone else. And thank you all for being here. I know it's confusing to be here on a Thursday and yada, yada, yada. Okay, so today we are actually, there are two equations written on the board here. The first, you might have noticed, has been written. This is like the third time I've written on the board. We are finally actually going to get to it today for real, comma, yo. The second one we're also going to get to today, and in a weird way, and we're sort of going to get to them in a weird order, but we're both going to get to both of them today. So by the end of today, we'll have a total of 3 equations in this class. And today we're finally going to discuss homework 4, the average acceleration homework. Again, if for whatever reason you could still do it. I still have to get it back to you, blah, blah, blah. But homework 4 is what we're going to discuss today. Also, side note, homework 5, which was posted and which was in theory made to be due a week from yesterday. I was then reminded, or I then remembered that that's an inappropriate day to make things due. So it got rescheduled to be due a week from tomorrow. Just to be clear, that's not a class day. And I'm still not being strict with deadlines at this point anyway, but in principle, it's due the Friday, a week from tomorrow. Homework 5 is. What we're going to go over today is homework 4. And let me just preface that by saying, and you stop me anytime with questions or whatever, that homework 3 is what we discussed like 2 classes ago. Then, we discussed it as a group. Then yesterday, I tried to give a sort of big dump, verbal dump regarding the takeaway of homework 3. The takeaway is Galileo's principle of relativity, right? That is a principle that can be said many different ways, and each different way that it's said has different other implications. And we ended up yesterday by writing it down in 3 different ways in English: form 1, form 2, form 3, and you're responsible for all those. And then we got to form 4, which is mathematical looking. There are still at least 5 more forms that we do in this class. Each next form of that principle, in a way, is yet another topic or chapter of physics. Like each next development that occurs in physics comes from that principle, one way of stating it or another. Sometimes the ways of stating that principle are mathematical, sometimes they're not. But all of it is an analysis of what velocity really means. In other words, and the big takeaway, so the big takeaway that ultimately, that first for you guys came from a like artificial, hypothetical imaginary thought experiment regarding a fictional train, like that's how we all were thinking of it. But then that we realized was a big analogy to a very actual real world situation called Earth. And what I'm arguing is that for hundreds and thousands of years, people really did legitimately debate and wonder whether the Earth actually was moving or not. And if so or not, what evidence did we have in either direction, or how could we prove or derive or convince ourselves whether the Earth was or was not moving? And once we did, how could we account for the many seemingly persuasive counter arguments from the other side? Like, so I'm saying that there was a legitimate question for centuries as to whether the Earth was stationary or not. And the ultimate resolution, or the most recent historical resolution of that question, came in the form of Galileo's principle of relativity, which ultimately says, in a million different ways and with a million different implications, ultimately the principle says that velocity, and you may want to write this down, if please do write this down, I guess. The takeaway of everything we were saying yesterday, and this is going to come up again and again in physics 203, in physics 204, in physics for the rest of your life, and science for the rest of your life, is that velocity is a relation between two objects always. It is never a property of one single object. Velocity is a relation between two objects. It is never a property of one single object. That's our takeaway. Or put another way, velocity is always a comparison. Put another way, velocity is always relative. The velocity of thing one makes no sense unless you say as compared to thing two, like always in physics. Quick side note, anything you've ever heard, for good or for bad, like on PBS and Nova or New York Times or Scientific American, anything you've ever heard in the culture about like 20th century physics, about like Einstein, about like the special theory of relativity, or Einstein and the general theory of relativity, or like twin paradoxes, or things going close to the speed of light, or time bending, or space curving, or like any of these, or black holes, any of these crazy things that some of you might find super interesting and some of you might find super weird, or whatever, all these things that you ever hear about in modern physics that come from Einstein and come from relativity, what I'm telling you here is they first originate in Galileo's principle of relativity. And that's explicit. Einstein, in his 1905 paper that first introduced the special theory of relativity to humankind, like in his 1905 paper, he literally quotes Galileo, and he puts forth the two basic postulates or premises on which all of modern relativity rests. And he says one of them, of the two ideas that he puts forth for the rest of the century, that gives us all this weirdness and all this exciting stuff that is known as modern physics. Of the two statements that he puts forth, the first one is literally Galileo's principle of relativity, and he attributes it to Galileo. There's no question about it. And the second statement, for those of you who care, has to do with the speed of light always being constant. So this principle of Galileo's is central to physics. Everything that's done in physics from 1626 on, in one way or another, comes back to this principle. And what the principle is you can't talk about the velocity of one object without comparing it to the velocity of another object. And by the way, conversely, depending on, if you choose a different, if you want to know what the velocity of Earth is compared to the sun, you'll get one number. If you want to know the velocity of the Earth compared to Jupiter, you'll get a different number. If you want to know the velocity of the Earth compared to Earth itself, you'll get another number, which is 0. And each one of those numbers is equally correct. Velocity is a matter of perspective, of frame of reference, of coordinate system. That's, and again, I'm not trying to get myself all bogged down, but that's like the big takeaway from yesterday. And it's a big, important thing to understand about velocity before we get any other equations about it or do any other math with it. Now that's from yes. Okay, so it's going to keep coming up. It's a way of understanding the nature of velocity. However, today we're going to get another equation about velocity. Like in a way, it'll be our third equation involving velocity, and we're also going to get an equation about acceleration that has velocity in it. So we're going to get two more equations today that refer to velocity, and it's like, and I don't want you to think that they're redundant or contradictory. Physics is all about motion. Velocity is the simplest expression of motion through space and time. So we have a lot of references to velocity in a lot of equations, and that's not a coincidence. We're going to get to these two equations today. Now that I've just attempted, hopefully, to kind of summarize what the takeaway of yesterday is, I'm going to say you can somewhat put that to the side of your brain. Like that was all from homework 3. That's all the conceptual underpinnings of velocity. We're now going to move on and be a little bit more mathematical again and get to homework 4. So you don't kill yourself looking for direct applications from homework 3 in homework 4. It's kind of two different ways of talking about velocity. Don't try overly hard to connect the two. We're going to go to homework 4 now. We're going to be a little bit more mathematical. And I'm going to switch so homework 4 is where we're going to, you can stop me still with any questions about homework 3 or anything, but we're going to homework 4 now. So I'm flipping that, I'm flipping the page. Hold on. Okay. And I'm going to be flipping back and forth between like on my screen, I'm just sharing the board, but I'll be looking at the homework like on another window on my computer. So please do, so I can't see your faces sometimes. So definitely put anything in the chat if you need to stop me or go back a page or anything like that. All right, so we're going to homework 4. So and also please have homework 4 out in front of you while we're doing this, like the questions. Okay, so homework 4 called average acceleration. All right, little warning here that ends up being said. I'm just warning you here that I'm not necessarily always making the 5-step solution clear in what I'm doing here. I'm now just trying to talk about material. I'm leaving it up to you to be tracking the 5-step solution. Okay, so Roman numeral 1, very quick review. It says we got Berlin, 700 miles north of Rome. And I am providing a quick diagram here as in step 1 DFP. Here's my quick diagram. And, you know, you almost might think, okay, like really, is that diagram really necessary? The most necessary thing about this diagram is I'm making a decision right in my diagram. So again, I'm on Roman numeral 1 of homework 4. In my diagram, I am making it explicit that I'm making a choice to call north positive and to call south negative. Let me stop right there and say that is a choice. It is, you could call south positive and you could call north negative, but direction definitely matters. Direction is going to affect the negative or positive signs that we get in our answers. And so according to Galileo, okay, Galileo is saying motion depends on frame of reference. All the laws of physics are the same in all unaccelerated reference frames, or in other words, all the laws of physics are the same in all coordinate systems, right? This is Galileo. So you might choose a different coordinate system. You might say that north is negative and south is positive. And if you do that, like in your homework or like in your life, and if you do that, you're going to get answers. Some of your answers are going to be slightly different from mine. We'll see on the next page if you do that. As long as you labeled your coordinate system and you consciously chose your coordinate system, if you get different answers from mine, what Galileo is saying is your answers are just as valid as mine. The laws of physics work in a coordinate system that's pointed this way as they do in a coordinate system that's pointed that way. Okay, your answers are just as valid as mine, even if you chose to turn your coordinate system like this. That's the good news of Galileo. the laws of physics are the same in all unaccelerated coordinate systems. However, the downside of Galileo is, and this is one of the reasons you must always include a diagram in every one of your homeworks, is that either choice you make is okay, but you have to make a choice. You cannot, it's not a choice to not make a choice. It's not like voting in America or in Florida or something like that. Like you have to have a coordinate system. You have to be in a frame of reference because velocity is relative to frame of reference. So you could choose Earth or you could choose Sun as an example, but you can't choose not to choose because it's all, everything is a comparison. So I've chosen to call, so the point of my diagram is to make it clear from here on in, anything that's north, I'm going to call positive. Anything that's south is I'm going to call negative. And I'm going to base my answers on that. So I turn the page. Okay, so it says, so the woman, so it's a quick facts. The woman flies from Berlin to Rome. That is, she flies south and it's 700 miles. So question A, what's the distance equal? So I didn't put in much work here. I apologize, but I wrote my answer is distance equals 700 miles, like according to the diagram, right? I mean, it's not a trick question. It's just she flew 700 miles set to the south, but it's just asking distance. So it doesn't care about direction. Then it says in B, what's the displacement? Now I probably should have put in a GDP, or I kind of skipped steps. Again, remember I warned you, these are kind of just answers, not full solutions, but the displacement is negative 700 miles. That's a negative sign there. If I chose a coordinate system where down is negative, where south is negative, then her displacement is negative 700 miles. If you chose reverse, if you made south positive, then fine, then your answer is positive. That's okay. But if you didn't make a choice, if you didn't make a coordinate system and label it, and you just wrote displacement of 700, then like truthfully, that's wrong. And stop me if that doesn't make sense. But so, okay, this is all in the spirit of Galileo now. So we sort of are using the Galileo thing. Then see what's the average speed. Okay, average speed triple equal GDP, average speed triple equal sign equals distance over time. So average speed, I plugged in the numbers here, 700 miles over 4 hours that says 175. It looks like 0.75, but that's 175 miles per hour is the average speed. That's the answer. I'm sure everybody did get that answer. Hold on, I'm just fixing that. Okay, that's 175 miles. Okay, so now I go to the next page. Again, stop me if you want me to go back a page or something. Now, indeed, ask for average velocity. Now we're getting into like a vector quantity that cares about direction. And we have mathematical symbolism for velocity. So average velocity is average velocity is displacement over time. The displacement, strictly speaking, she went south. So strictly speaking, she went from 0 to negative 700, whatever. So I get a displacement of negative 700 miles over 4 hours. So her velocity is negative 175 miles per hour. Again, if you had a different coordinate system, then you might have gotten positive answers for these two. But I'll tell you this for sure, if you got negative 175 for the displacement, then absolutely you have to get negative 175 for the velocity. And this is just a quick review, but it's also a quick reinforcement that that velocity absolutely can be negative. And when velocity is negative, that doesn't mean it's Michael J. Fox or a flux capacitor or, Back to the Future. It doesn't mean anything psychedelic or weird. It just means she's going south. Positive would have been north, negative means south. So it's literally just a mathematical shorthand for saying she went 175 miles per hour that way. Okay. So just a review to remind us that velocity could have a negative sign, and that's totally okay, and sometimes required. All right. So that's the answer to that. Please stop me if anything's unclear about that, but that's the answer to that. Then next question, instantaneous velocity. Okay, so the next question asks this thing. It presents a car, and it asks you this weird question. It asks it gives you some facts, and then it asks, what's the instantaneous velocity at like the 18th minute, 42nd second, or something weird. But it sounds like very obscure, and it sounds like, wait, how? I mean, what math do I have to do to use all that information? Okay, so first of all, I want to back up and say this problem is the first time that we're referring to a concept known as instantaneous velocity. This is our introduction to that concept. We've been talking about velocity up until now, but any equation that we have for velocity is an equation for average velocity. Okay, that's different. What we're talking about now is instantaneous velocity. That's, as it says on the sheet here, that specifically means velocity at an instant, velocity at a point in time. That is different. Yeah, that is different from average velocity. Sometimes the V that we're using here will have an arrow over it. Sometimes it'll have an arrow, as you see at the bottom of the sheet. Arrow, as it's trying to say, arrow is a reminder that this is a vector quantity. If you ever see an arrow over a symbol, that means it's a vector quantity. That's a reminder that magnitude and direction both matter, as in our context right now, like as in minus signs do matter. That's not the same thing as a horizontal bar over a symbol or over a variable name. It's not the same thing. The bar means average. No bar or even an arrow means not average, means at a point. So I'm making it clear here at the bottom of the page. I'm trying to remind you now, V with a bar over it, average velocity means displacement over time. When we originally wrote it, we wrote it with x minus x naught at the top and t minus t naught at the bottom. Now, a lot of times we cross off that t naught because t naught means what the time was when our experiment started. And generally that means when our experiment starts is generally when we start our stopwatch. So we generally call that 0, so we can cross it off, call it 0, and we don't have to worry about it usually. But I'm putting it back in for a moment just to make a point to show you average velocity. And this is what it says in red on the side here. It's hard to see. It says average velocity refers to an interval in space per an interval in time. Average velocity is the separation between 2 points in space divided by the separation, the region, the difference, the separation, the interval between 2 points in time. Average velocity assumes that you've got 2 different points in space and time, and in your mind, you're thinking about a gap between them. That's what average velocity assumes. But instantaneous velocity is asking what's going on at one of those points. At one of those points, not between 2, but at 1. That's a very different type of question. So let's be clear about this for a minute. Like instantaneous velocity. So I'm saying instantaneous velocity is a very different kind of question from average velocity. Instantaneous velocity, we all believe in, whether we've thought about that word or not before, we all deal with in life all the time. Like if I'm driving down the road and then I come to a sign says school zone, 20 miles an hour, and I go flying past that, I would never do this. But if I went flying past a sign that said school zone, and then I get pulled over by an officer of the law who graduated from John Jay, and they don't recognize me, and they pull me over. No, they're doing their job, and they pull me over, and they say, "Hey, buddy, hey, long-haired freak, what? Do you know how fast you were going just now when you just passed that? Did you see that sign that said school zone? Right when you passed that sign, you know how fast you were going when you passed that sign?" If they say that to me, right, which is a very reasonable question, like a super reasonable question and a super common question that we've all faced in one way or another, first of all, I don't say to the officer, "Huh? What do you mean how fast I was going at a moment? Like, what do you mean? Like, I don't have a formula for that yet." Like, I don't say that. Like, I know exactly what he means or she means. Also, what I don't do is I go, "Oh, that's a very good question, officer. Well, you happen to be in luck because I happen to be a physics professor. So let me tell you, I'll tell you. You want to know velocity? I'll tell you velocity. I've been in the car for 3 hours, it turns out, okay? And I left my house like 3 hours ago. And during that 3-hour time, I've done a total of 60 miles. Okay. Now, granted, I pulled over to use the bathroom twice. And granted, like a couple of times I realized I was going the wrong way. So I backed up and reversed and turned around. And I did. But then a couple of other times I passed some people in the left lane. Like, granted, I was doing all these wacky things. But I could tell you for a fact, officer, that I've been in the car for 3 hours and I covered a total of 60 miles in those 3 hours. So 60. So let me tell you how it works. I'm a physics professor. displacement was 60 miles, time was 2 hours. Time was 3 hours. So 60 divided by 3 is 20. So clearly I was going 20. So I don't see what the problem is, officer. Like, I hope you followed that. And I hope you followed that everything I just said is true about average velocity. But that would be a crazy, obnoxious, stupid, rude, and self-destructive thing to say to an officer who pulls me over and says, do you know how fast you were going when you just passed that sign? Because they don't mean any of that, right? That would just be ridiculous of me to do that. Like, they don't mean on average, how fast were you going for the last 3 hours? They mean how fast. So in other words, they don't mean how fast was I going between two separated points in time and space. They mean how fast was I going at a point in time and space, the point when I passed the school sign, right? That's what they want to know. And it's a very reasonable question, and it's a very common question. But it's true that if I started plugging in numbers to that, based on the equation that we have so far, I would not get the right answer. Like, I might be going on average 60, but sometimes I was going a lot slower, and sometimes I was going not at all, like I was, at a rest stop. And sometimes, therefore, to compensate for that, I was going a lot faster. And they want to know one of those times what I was doing, right? Now, if we just plug in to x minus x naught over t minus, which people do all the time in homework and exams and stuff, but for instantaneous velocity, if you just plug into x minus x naught over t minus t naught, if you really think about it, t minus t naught, like the difference between the two moments in time would be 0. Like, they just want to know a point in time. So you would plug in 0 into the denominator. And if you ask yourself, how far did I get for the numerator of the fraction? If you ask yourself, well, how far did I get between, like, not between 301 and 303, but just between 302 and 302 itself, like just at 302, how far did I get? Well, the denominator would be like 302 minus 302 would be 0 in the denominator. And in the numerator, I put 0 because I didn't get anywhere at 302. At 302, I was at a place. I wasn't getting anywhere. I didn't get anywhere. I just was somewhere. So if I just plug into that equation, I would get 0 over 0. And that's crazy. That's another thing I'm not going to tell the officer. If the officer says, do you know how fast you were going when you passed that sign? I'm not going to say, well, at the moment I passed the sign, no time passed, and I didn't get anywhere. So I guess I was going 0 over 0, sir. Like, ma'am, I'm totally not going to say that. First of all, that's obnoxious and irrelevant and not what they're asking. But second of all, let's say they even are a physics professor or a math professor or like took physics at John Jay. They know enough to know that 0 over anything is always 0. And anything over itself, like 7 divided by 7 or 4 divided by 4 or 1 divided by 1 or x divided by x is always 1. And also anything divided by 0 is always undefined or infinity, right? So if I say 0 over 0, what kind of crazy answer is that? But that's what the equation would return. 0 over 0, literally 0 over 0 means 3 contradictory things at the same time. It means 0, it means 1, and it means undefined infinity. That's crazy. So we can't just use the equation to get instantaneous velocity. What are we going to do? The only way to know what you're doing at a moment is to look at the larger context surrounding that moment. That's going to be the answer. Now, ultimately, we'll have an equation or a mathematical way of doing that. But let me tell you that this is a very instantaneous velocity is more common, more important, and more precise than average velocity, but it's also a lot harder to actually think about or compute. To get instantaneous velocity, we're always going to have to somehow or other look at context, just like to know if you took a movie. Well, I'll leave it at like, so here's what we do. So the next page. So how do we compute V? Now remember, I'm putting V with an arrow over it. Arrow just meaning vector, as opposed to V with a bar over it, average. How do we compute it? Well, ultimately, we need a way of looking at V in context. That's what this says. Ultimately, we need a way of looking at V in context. So for example, we have this example in the problem that they're giving us. So I'm still in homework 4 here. I'm on Roman numeral 2 of homework 4. It says, example, this car, they tell us about a car that's traveling at constant velocity. Now they give us a couple of numbers. They say it travels for 40 miles and they say that it travels for 30 minutes, or in other words, a half an hour. So I wrote those. I don't know why I converted it to a half hour. You don't have to do that. I just did it because I'm thinking miles per hour. You don't have to do that, but I converted half hour to, I converted 30 minutes to half hour. So I wrote down the facts at the bottom of the sheet, 40 miles, half hour. But then I also wrote the super important fact, and I wrote it in equation form. They said the car travels at constant velocity. So from here on in, if you ever want to say, remember, V stands for velocity. And remember, if you put a naught, if you put a subscript 0 to the right of something, that means the value of that thing at t equals 0, the value of that thing at the very first instant of the experiment. So from here on in, if I ever write V equals V naught, like I've written here, V equals V naught, that's a symbolic, mathematical, scientific way of saying V doesn't change, right? Like I'm literally saying V at any single moment is the same as what it was at the very first moment. That's a mathematical way of saying V doesn't change. And I think that's a very important fact for this problem, that V doesn't change. I'm going to use those facts to figure out, like, it's asking me how fast is it going at the 18th minute, the 42nd second. So what do I do? All right, go to the next page. So, all right, so it's asking, what is the velocity at t equals 18 minutes, 42 seconds? Again, for some reason, this is so stupid, but just because like I converted to hours because I wanted to have things in miles per hour, I converted 18 minutes, 42 seconds to say that that equals 0.32 hours. I mean, you don't have to do that. I was probably making it confusing than I did, but I did. So the question is, at t equals that weird moment, that seemingly crazy or, intimidatingly strange moment, what is V? Well, what I first used the equation. I used our one definition of average velocity, right? I used V bar triple equal sign x minus x naught over t. Okay, I plugged in 40 miles for the displacement. I plugged in 0.5 hours, or in other words, 30 minutes for the time. I divided and I got 80 miles per hour. Now I want you to look and see in the middle of the page here, I have 80 miles per hour. But I just want you to notice that I didn't circle that yet. Like, okay, honestly, do I think that's ultimately going to be the answer to this question? Yes. And did a lot of you people get that the answer is 80? Yes. But let's make it very clear that just dividing 40 by 0.5 hours, like, I'm not done yet just because I see an 80. Like what I've just gotten, what I'm trying to say is there's a reason I haven't circled the answer yet. What I've just gotten with this 80 is I've gotten the average velocity. And okay. Oh yeah, cool. Thank you. Got you, private chat person. Got you. Thank you. Totally appreciate it. And I know it's Thursday, so things are weird. Yes, thank you. Oh, and you warned me too. Thank you. Totally appreciate it. And put that in for participation. Okay. So so like what I'm trying to really say here in a strange way is I'm trying to say over and over again that velocity at an instant does not mean the same thing as average velocity, like triple equal sign with a slash through it. I'm saying they don't mean the same thing. How fast you're going on average does not mean the same thing as how fast you're going at a moment. How fast you're going at a moment is going to require some thought on our part. But now in this case, and I'm not saying you can't use average velocity to get it, but you're not done just automatically just once you get average velocity. So we used average velocity here and we said the average velocity for this thing is 80 miles an hour. Now we want instantaneous velocity. How do I go from average to instant? Well, in this case, hold on. In this case, In this case, we are told that the instantaneous velocity never changes. In this case, we are told sorry. It's weird, I thought. Okay. In this case, we are told. Sorry. I'm just trying to. This is weird. Didn't someone just? Okay. All right. In this case, we are told that the velocity never changes. So in this case, we can say, oh, since the velocity never changes, it must always be the same as the average. In other words, so we say in this case, the instantaneous velocity at any moment, at every moment, I don't care whether it's 18 minutes, 42 seconds or 19 minutes, 39, like even though it sounded like the question was asking us some very obscure, strange moment in time that you might think that you have to plug in somewhere. And in fact, some of you did. Some of you plugged in 18 minutes, 42 seconds as the denominator of the velocity fraction. Like, I understand why you did that, but no, don't be fooled. Don't be tricked. Like that's no, like the point is that the average velocity is 40 divided by 0.5 hours. So the average velocity in general is 80, but then we're told that the velocity never changed at all. So what this is, therefore the answer is 80. What this is just like, now this does not answer. So what I'm trying to say is in this first simple case, here's the first simple case where we can get instantaneous velocity by looking at the larger context, by saying, okay, for the larger context of this whole journey, we know an average. And for the larger context of this whole journey, we know that the point-wise velocity, the instant velocity never changes. Therefore, we're going to believe that the instantaneous velocity at any moment we choose is the same as the average. So we're good. Then that particularly only relied on the fact of this particular problem. That's not an equation yet, or a method that's not going to work every time. The one piece that is going to work every time is that we're looking at the larger context. Okay. So what I'm saying here is this is like, if I walk up to you, or I walk up to my older son and he says, Dad, I had 5 exams in my Shakespeare class and I have a 95 average in the class. Do you happen to know what I got on my 4th exam? Right? If my son says to me, I took 5 exams, I have a night, and these numbers are fictional, by the way. But he is in a Shakespeare class. I'm so proud of him. Okay. If he says, I took 5 exams, I'm in a Shakespeare class, Shakespeare's not relevant. Why am I? Okay. I took 5 exams. I have a 95 average. What did I get on my 2nd exam? I can't tell. I don't know. Right? All he told me was his average, and he took 5 exams. I have no idea what he got on his 2nd exam, right? On like some of his exams, he might have gotten lower than 95. On some, he might have gotten higher than 95. And if you really think about it, and if you know how your grades were, you know that's totally possible he has a 95 average and he never once got a 95 on one of those exams, right? That's actually possible. So if he just says to me, my average was a 95, what did I get on my 2nd exam? I say, I have no idea, yo. And that would be like this problem. If you say the average is 80 miles an hour, what was the speed at the 42nd second of the 18th minute? I have no idea, yo. But if you, but if you say, if my son says to me, I have a 95 average in the class, I took 5 exams, and by the way, Dad, I got the same score on every single exam. If he said that to me, that's like this car saying this car is going constant velocity and his average is 80. Oh, if my son says I got the same on every single one and my average is 95, oh, then definitely he must have gotten a 95 on every single one. And stop me if you don't understand that. I mean, I think you do, but stop me if you don't understand that. That's just like this car. If we needed to know that the car was going constant velocity, that it never changed its velocity. Since we knew that, then once we got its average, we say, aha, its average is what it was doing every single time because it never changed. So we got 80 as the answer for this one. Okay, bottom line, the answer is 80, but you really have to say something. You can't just say it's 80 just because the average is 80. It's because the average is 80 and the velocity was constant. Okay, so that's that one. But now what if it's a little bit harder? What if, like, what are we going to do? I'm just looking at the time. What are we going to do, comma, yo, if velocity is changing? Like, what are we going to do if something's actually speeding up or slowing down? What are we going to do if it's changing velocity? Okay, we need to think a little bit more. We're still going to look at context. We're still going to look at some kind of pattern or something that we can rely on from context to figure out instantaneous velocity, but it's not going to be quite as simple as this. So let's turn to the next page. Okay, so right, so what if v doesn't equal v naught? What if velocity is changing? So how do we compute v then? So the first thing I'm saying here in the middle of the page is when velocity is not constant, we call that acceleration. That is what acceleration is. It literally in physics, acceleration is change, like triple equal sign, right? In English, acceleration is change in velocity per time. Now, of course, I'm going to give you an equation for that in a moment. It'll be our second equation of the semester. Woo! But before I, write it as an equation or write it symbolically, first of all, I just always want you to know that these equations they're not just formulas that are pulled from nowhere. They're just symbolic translations of concepts that hopefully actually make sense in English. And often I think the concepts make sense in English because they're just definitions. They're just the meaning of words. Acceleration in physics means change in velocity per time. Now, before I turn the page, note, velocity means speed and direction. Speed and direction. So one thing you might want to note as a sidebar or something is, in physics then, acceleration means change in velocity per time. That means change in speed and or direction. In physics, if you are speeding up or slowing down or turning, then you're accelerating. Acceleration literally means any combination of speeding up or slowing down. Like that's called acceleration also in physics. It might be called negative acceleration depending on how your signs are arranged, but it's called acceleration. Or turning. That is an acceleration as well in physics. Acceleration is any kind of change in velocity per time. So to write it as an equation, we write it like this. It looks just like an equation that we already have, the only equation we already have. We have that average velocity is defined to be change in position per time. Well, just like that, we're now going to say from here on in, average acceleration equals change in velocity per time. It is not the same equation. It's not the same concept. It won't yield the same units or the same numbers, but it absolutely is analogous. It absolutely is a parallel. It's not a coincidence at all that the two equations have such similar or identical structure. Like note, before I go on the page, note is on the left-hand side, whatever we're defining on the left-hand side of each of these equations has a bar over it, meaning average, meaning on the left-hand side, we're looking for some kind of rate of change between some kind of average rate of change between 2 points in space and time. The first equation is having us look at average velocity from here to there, from now to later. And average acceleration, the second equation, is having us look at average rate of change of velocity from now to later, or from here to there. So on the left side, it's an average. It's an one value that describes an interval between 2 points. But on the right side, we're actually subtracting 1 point from another. We're actually getting the difference between those 2 points, in the numerator and in the denominator. And again, just like before, just to be clear, hang on one second, like we could write minus T naught. We could, you know, so that you can see the parallel structure, you could put a T naught in there, and then you hopefully see how really sort of symmetric all of this is. But T naught always equals 0. So like we usually leave it out. But, you know, it's just a ratio of points to points in time. And now what I'm saying is it's not a typo. It's not a coincidence that on the right-hand side, there are no bars in the numerator. There are no bars on the right-hand side. There are bars on the left-hand side. So average velocity is the change from one point in space to another per point in time, from one position to another. So the units of the top are meters, and the units of the bottom are seconds, right? But then for the second equation, we're looking at the difference between one instantaneous velocity at one moment in time to another instantaneous velocity at a moment in time. In other words, the units in the top here are meters per second. The units in the bottom are still seconds. So we're invoking, so it's like meters per second is what we're talking about for an acceleration. But the key point I'm making is that it's not the difference between two average velocities. It's the difference between how fast you're going now versus how fast you were going then. Velocities at two different instants. Now, how does that help us? If you're following this, yeah. What I'm saying now is, if we want to now deal with situations where instantaneous velocity actually changes from moment to moment, if that's what we're trying to get into here, like recognizing that your velocity could be one thing now and another thing a little bit later, and if we want to get into that, which we do, the concept is called acceleration. Acceleration is change in velocity, but it refers to the kind of velocity that we still don't have an equation for, right? Like acceleration means change in velocity now versus velocity later. And you might well, if you're following this, you might well be saying to yourself, okay, but did we figure out how to get instantaneous velocity like now or later? Like, isn't that the whole thing that he said that we haven't figured out yet? Right. If you're a little bit like looking for how to fill in these individual V's, you're right. So I'm saying one way now is you can rearrange this equation. So it says in my handwriting, my illegible handwriting says, thus, one way of computing V, because that's what we're looking for, right? We're looking for how do you compute velocity at a moment? One way of computing V is from the context of average acceleration. Like in the first example that we did a second ago, we used the context of constant velocity. But maybe that's too simple. Maybe that doesn't describe most situations. Maybe a lot of situations you're not going at constant velocity, you're accelerating. So I'm saying, say if you know the rate of acceleration, then you can rearrange this equation and solve for V, right? That's one way. Like, so for example, this is not on the page. I'm just saying it. I'm just looking at time. Okay, we still have time. Okay, so I'm saying, for example, say that car, the car from the last example, it wasn't always going constant velocity. Say it wasn't always going 80 miles per hour. Say it was accelerating, but say it was accelerating at a reliable average or even say constant rate, like in a pattern. Like let's say that the car starts from rest, but then it gets up to a speed of 80 miles an hour in an hour. And then let's say in the next hour, it gets up to 160 miles per hour. And then in the next hour, it gets up to 240. I mean, that's very fast, but 240 miles per hour. In other words, let's say it has an acceleration rate that is steady and constant and quantifiable, and we know it. Let's say its acceleration rate is 80 miles per hour, that every hour it's gaining speed of 80 miles per hour. This would be an example of an acceleration, of a constant acceleration. And if we knew this was happening, this is a fresh example, I'm just saying I'm just saying in this discussion, say we knew something wasn't going at a steady velocity, but it was gaining velocity in a steady way. If we knew that every hour it gained 80 miles per hour of velocity, then we would say it has an acceleration rate of 80 miles per hour. Like notice again, or if you don't like, or meters per second, we would say if it was gaining 80 meters per second of velocity every second, we would say it has an acceleration rate of 80 meters per second. Like second would come into it twice because we have meters per second in the numerator of the definition, and then we have seconds again in the denominator. It's change of velocity per time. So you could even abbreviate that, and you may remember this from high school. You may have heard of this in high school or somewhere else, that if we're talking about a velocity, we say something like 80 meters per second. But if you're talking about an acceleration, you say something like 80 meters per second squared. Again, we don't mean Michael J. Fox. We don't mean flux capacitor. We don't mean some weird thing of squaring time. Whoa, no, we just mean seconds times seconds in the denominator. We just mean meters per second per second. So if we knew that the acceleration rate, if we knew the acceleration rate was 80 miles per hour, in other words, 80 miles per hour squared, right? If we knew that, if we knew the A, if we knew the A, and we knew, let's say that it started off at rest, and then we knew how much time it had traveled. If we wanted to know how fast is it going at the third hour, we could use this equation to say, oh, well, it's gaining 80 miles per hour of velocity every hour. Its acceleration rate is 80 miles per hour squared, and it's been doing that for 3 hours. So at the end of the third hour, it's at the moment of the end of the third hour, its instantaneous velocity is 240 miles per hour. That, right? That would be another way of getting instantaneous velocity, even when the instantaneous velocity is changing all the time, right? Notice I'm about to turn the page, I'm about to move on, but just please notice that this is in the case of a slightly harder example than the original one, we still could get instantaneous velocity. We're not assuming the velocity is always the same. We're assuming the velocity is changing in this case, but if it's changing in a steady way, then we could use this equation to get instantaneous velocity. So I'm going to pause for a second. Just please note, so far then in this class, for whatever it's worth, we now have 2 equations in this class: the V bar definition and the A bar definition. Definition of average velocity is one of our equations. Definition of average acceleration. They're actually both more powerful than they might look like, but that's what we have so far, 2 equations. Now I'm going to turn, we're going to go to the last page. We're doing well here, actually, let me just make sure, I know I've been like yelling. We have one more page to do, and I want to get back to homework 4. And we're not going to finish homework 4 today, by the way. We're going to finish going over it next class, but we're still going to make more tracks. Let me just make sure. Can I just get an electronic show of hands if you're clear and with me so far? Like if you're with me, if you're here, cool. Oh, that was fast. I love this class. That was really fast. So you're okay. Thank you, Gianna. Thank you, Al-Smail. Thank you, Abdel. Thank you, Stephen. Thank you, Jose. Thank you, Brian. Thank you, Brianna. Thank you, Montserrat. Thank you, Sarah. Thank you, Anthony. I think awesome. So those people who all just raise their hand are saying that they're hearing me right now and things are basically clear, basically. Could I just, thank you for putting that. But now, just because not everybody raised their hand, I'm just going to do the control of the experiment, so to speak. This is the last time I'm going to just put up your electronic hand right now. Just if you hear me, please, everybody, just put up your electronic hand if you hear me at all right now. It's kind of obnoxious on my part, but that's just almost everybody. Keep them up for a second. Wait, does everybody hear me? Well, this is okay. This is why I don't want to call anybody on. Everybody who's hearing me is putting their hand up. Thank you. And everybody who's hearing me at all right now, everybody who's in the room at all is putting their hand up right now. It's not a test. It's not to be obnoxious, but I just want to make sure. Okay. I don't want to single anybody out. But okay, cool. All right. All right, so I'm going to move on now. cool. Thank you. You can put your hands down. Thank you. I know that's like dicey that I just did that, but I am going to take that to mean that the stuff is clear right now, right? Maybe, and again, whenever it's boring, that okay, at least probably hopefully means it's clear. Because I could make it very exciting, but then it could also be confused. So, oh, but Alejandro, do you have a question, or are you just keeping your hand up from before? Or is that a question? Or are you still, you can put it down if you don't have a question, but oh, and Kay is back. Okay. Oh, Kay is it? What kind of dog is that? Oh, sorry. Okay. You'll meet my dog too at some point too. Okay, but anyway, okay. So I'm turning the page. I want to start solving some problems. I want to get back to homework 4 and solving problems, but we still have 20 minutes, which is good for me, maybe a drag for you. But there's one more thing I have to say before we solve any more problems on homework 4. One more page I have to do, and that is, okay, I just said this is one way you can get V, like if you have a value for A. But you might say, what if we don't have a value for A? Like, then what do we do? Fair question. I mean, because sometimes you don't have a value for A. Or you might even say, if you want to be a little bit deeper about it, you might even say, well, okay, I guess I could get A, I could get V, as long as I know that there is a steady acceleration. But like, forget about whether I have the value or not. What if there just isn't a steady value for acceleration? Like, what does V really mean in general? What is there an equation or formula or whatever for instantaneous V? So here's what it is in general. And this will make some of you happy and maybe not make others of you happy. What I'm saying on this next page is like, what is V really? Like, what is the definition of instantaneous V for all contexts and all times? Like, if I release any restrictions, like again, we start with the simplest concept where velocity was constant. There was no acceleration at all. Acceleration was 0. Then I went to a slightly harder context where velocity was changing, where there was an acceleration, but acceleration was some known number that was steady and constant. And I kind of showed you how to get V for each of those contexts. But what is V in general? Well, what V is the limit. What V without a bar on it is the limit of V with a bar on it. Okay, this is suddenly going to look a little bit like calculus. Not a coincidence. There's a reason that you had to take calculus to take this class, for good or for bad. What I'm saying is, so what I've written here in black, I've written 3 or 4 different ways of saying what the true definition of instantaneous velocity is. If any of these 4, they're all equivalent. The 4 things I'm writing here are all equivalent. If any of them makes any sense to you or works for you at all, go with that in your mind. Like seriously, they're all equivalent. They're just different ways of saying things. Some of them might click for you. I'm saying that I'm saying this. Oh, sorry. Okay, I'm saying if you have some graph of something's position with respect to time, something's moving somehow in one dimension, and the clock is ticking. If you draw, like it might not be going in a constant, steady way. It might be going in some kind of curve, like, excuse me, It might be going in some complicated way, like this graph indicates, or maybe even in a more complicated way. The object might be speeding up, might be slowing down, might be sometimes speeding up, then slowing down. It might be reversing direction. It might be going forward. It could be doing any kind of complicated thing. But if you take any 2 points, like time 1, position 1, and time 2, position 2, and with a dotted line or in your mind, you draw a straight line between those 2 points, that straight dotted line does not necessarily represent what the object actually did. But if you take the slope of that straight line connecting the 2 points, the slope of that dotted straight line, the slope would be on average the rate of change of position with respect to time. If you took the slope, the rise on the x-axis versus the run on the t-axis, if you did like y2 minus y1 minus x2 minus x1, only instead of talking about y's and x's, you're talking about x's and t's, right? So you take that thing that you know from math and you just apply it to a xt physics graph, a space-time graph, rather than just a y-x graph. If you take the rise over the run, the difference in x values versus the difference in t values of the dotted line connecting those 2 points, you'll get the average steepness of that graph. You'll get the average rate of rise per run. In other words, if the graph is showing position versus time, you would get the average velocity. If you took the slope of the straight line connecting those 2 points, right? The slope of the dotted line connecting any 2 points on a position time graph would be the average velocity of the object. It would be on average how many positions it advanced per each unit of time, right? On average. So the slope of the dotted straight line connecting 2 points on a position time graph, and you please be writing this down somehow. Like I'm saying it, but please I'm saying the slope of the straight line connecting any 2 points on a position time graph is, the slope is the average velocity of the motion depicted by that graph, the average velocity. Now, what we want is not average velocity here. We want instantaneous velocity. We want how steep that graph is at a point, not between 2 points on average, but literally at a point. Like we might want the instantaneous velocity, say right here at this red point. Now, what I'm saying is, if this is like the cop pulling me over, the officer pulling me over, if I want the instantaneous velocity at that red point, I can figure out the average velocity. So in other words, on the graph, I want how steep the graph is at that point. Well, I could start by, I could draw the dotted line between 2 points kind of surrounding my red point, and I could get the slope of that line. And what that would be the average velocity between the 2 blue points. It would probably be close, like the slope of that line would be close to the steepness of the curve at my red point, but it wouldn't be exactly the same, right? So this is like when the officer asked me, how fast were you going right then? If I say, well, over time for the last 3 hours, I was going on average 20 miles an hour. Like that might be sort of close to what he's asking, but not very close. And I'll tell you this, if I picked an interval of 3 hours surrounding what the officer's asking, it's not going to be very close at all. If I wanted to come closer, I would say, well, over the last hour, I was doing blah, 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 blah. I think that's how fast I was going. Now, that still would not be the exact steepness of this curve. It would still not be the exact instantaneous velocity, but it'd be a lot closer, right? And let's get all the way down to business now. If I want to really actually be a fair citizen, a good citizen, like if the cop said, do you know how fast you were going right when you passed that sign, at that moment, that instant when you passed that sign? What I could say, or what really the officer might be thinking is, I'll tell you this, buddy, like your front tire, he might say, I was shining a laser speed detector at that sign when you passed it. It's like, so don't mess with me. I was shooting a laser there and I know how fast you were going. How would the laser tell him? What the laser would do is the laser would be a beam of light that as soon as my front tires broke that beam of light, a clock would start. Like for real. I mean, it's like a photo gate in the lab, which if you haven't used it, you're going to use. I can't remember if you used it, but like my front tires would break this beam of light that would stop a circuit and start a clock. Sorry. Okay, the clock would start. Then a very small amount of time, a very small but finite amount of time later, my back tires would pass through the laser and the clock would stop. So they would say in this very small amount of time between when your front tires went, or the front of the car, it doesn't have to be the tire, but whatever, you get, when the front of the car broke this laser beam, from that moment to the moment where the back of your car broke, like exited the laser beam and the laser beam was fixed, was repaired, we watched what your car did during that amount of time. We put that amount of time in the denominator. We, the computer hooked up to this laser, put that amount of time in the denominator of a fraction. And in the numerator of that fraction, we put the very small distance that exists between your front tires and your back tires. Because if you think about it, during that small amount of time that you spent crossing the beam, you went that small amount, like the beam in effect went from your front tires or your front of your car to the back of your car. So we took this tiny amount of distance that was covered by your car and divided by a tiny amount of time. And we got the average velocity for the tiny amount of time. In other words, we took these two blue points on this curve and we got them so super close to the red curve, to the red dot. We brought them so they're just surrounding that red dot. And we took such a tiny amount of time. We did an average in the limit as these two red dots got so close together that basically the amount of time between them was even below the threshold of anything you would ever care about or argue about. Or put another way, we made the amount of time so small that your car didn't have time to change its velocity, right? We took an average of the rate of, we took an average of your car's velocity over an interval that was so small that we're darn sure that that even if there was a change in the velocity, or even if there was an advancement in something, we couldn't even detect that with our measuring equipment. So we took an average over an interval between 2 points that was so small, it was below the threshold of measurement. We call that in math and in physics a limit. What instantaneous velocity is average velocity in the limit. It's what instantaneous velocity is the average velocity between 2 points in the limit as those 2 points get so close together that the interval between them is below the threshold of measurement. In other words, those 2 points are arbitrarily close together. They're far enough apart for something to happen, i.e. for a car to move. They're far enough apart that there is motion, that something's happened, but they're close enough together that we can't detect any change in what happened. So it's called a limit. That's anytime you've ever talked about limits in calculus, this is, I know in calculus, they always say it's as close as you want without actually being there. So they'll say in the limit as t approaches, so I'm like looking at the sheet now and I know we have 7 minutes, but I'm saying that instantaneous velocity is defined to be the limit as t approaches 0 of the average velocity. And what do I mean by the limit as t approaches 0? What I really mean is that t is big enough to be bigger than 0. It's big enough that there actually is a time interval there. So it's big enough that there are 2 points that we are measuring between, but it's small enough that the distance between those 2 points can't be measured, that the distance between those 2 points can't allow any change or variation or error to, or measurable error to occur. So in the limit as t approaches 0 means in the limit as t gets so close to 0 that we cannot figure out anything other than something happened. That's what, okay, that's my definition of limits. I'll say it one more time. The limit as t approach, because you've seen this, look, we've got 6 minutes. I know that you've all seen this in calculus before, but I also know if you're anything like me, or if you're anything like most of the students that I've had over 30 years, you've seen it in calculus before, but you didn't necessarily love it when you saw it in calculus. And then you did a bunch of stuff within calculus, but you never maybe necessarily, if you're like me, you did a bunch of stuff and you took derivatives, but you never really quite knew what you were doing maybe, or why, or when to do it. Or if you're like me, when you learned about this limit thing in math class, you might have accepted it, you might have done things with it, but in the back of your mind, you might have always been saying, limit as t approaches 0, you mean 2 points are so close together that they're almost 1 point, but they're not quite 1 point. If you're like me, you might have thought that I'm learning in a math class. Like that sounds like the most unscientific, unquantitative, unrigorous, unclear, weirdo thing. Why of all places would I learn that in a math class? I don't know what you thought, but if you didn't quite get limits or like them, you are not alone. And I'm not assuming that you did. What I'm ultimately saying here, with 5 minutes left, okay, to get to the punchline, I'm ultimately saying that instantaneous velocity is the limit as t approaches 0 of average velocity. What I really mean by that is, therefore, I'm saying it's the limit as run goes to 0 of a slope, right? I'm saying it's the limit as t goes to 0 of the change in x per the change in t. I'm saying it's a slope of a line connecting 2 points where the 2 points are so close that they're basically just 1 point. So the only way I could possibly measure the slope at that 1 point would be to draw a tangent line to that point. The only way I could literally actually get the exact slope at that line, I mean, at that point, the slope of the curve at that point would be to draw a tangent line. So that slope of that tangent line, the slope of the line connecting 2 points in the limit when those 2 points are arbitrarily close together, that is what's called derivative, okay? I'm ultimately saying that instantaneous, if you want a true definition of instantaneous velocity, the true definition is right down here. The truest, most universal, general definition of instantaneous velocity is that it is the derivative of x with respect to t, the derivative of position with respect to time. Now I have 3 minutes. Let me make, and I will go back to the rest of the sheet on Monday or whenever we next have class. But I hope I haven't lost anybody. I'm talking to there's at least 2 groups of you that I'm talking to at the same time, 2 different groups of you. Okay, there are those of you in the room, well, maybe there's 3. First of all, there's some of you that have heard this all before in high school and are like, yawn, I get it. Fine, good, I'm glad. So you could take a mental break and good, then I expect you to do even better with this when we have harder problems to solve. Okay, but then there's 2 other groups of you. There are those of you, maybe some of you, who are like, oh, okay, I didn't know he was going there, but I do understand derivatives, I think. So if he's saying that instantaneous velocity is just the derivative, the first derivative of position, okay, I get that. And I don't know why he didn't just say that 3 days ago. And if that's what you're saying, if it helps you at all to understand, if you understand your calculus and it helps you at all for me to say, here, this concept in physics is really a calculus concept, instantaneous velocity is the derivative of position with respect to time, then good. Like electron, bless you, and good. If this may, but for those of you, which I think is many of you, for those of you who are like, oh, calculus, really? Like, I mean, I can sort of do some problems and I sort of know the power rule and I know the product rule if you force me to, but like, I never knew like what they were talking about. And I certainly didn't like limits. And I never really knew what they meant by a derivative. Like I just like did stuff and got through calculus and I was sort of hoping never to see it again. If you are one of those people, first of all, don't be ashamed of yourself. I was one of those people too. Most people are those people. But if you are thinking to yourself, I never really did get calculus, so this does not help me, then I want to say to you, flip what I'm saying. With the 1.5 minutes I have left, flip what I'm saying. Instead of trying to understand the physics from calculus that you never liked, I'm saying this is an opportunity to re-look at the calculus. And maybe if you're like me, you might start actually appreciating or understanding the calculus for the first time. Because what I'm ultimately saying is instantaneous velocity is average velocity in the case where the average that we're looking for is over a super small time interval, like an immeasurably small, but nonetheless existent time interval. A time interval that's so small that you can't measure it, but big enough for things to happen and big enough for you to know it's there, but too small to put a number to. That's what I'm talking about when I say an instant. Big enough for you to know it's there and that things are happening, but too small to put a number to. That's what I mean by an instant. That's what I mean by a limit. That's what I mean by instantaneous velocity. And that's all derivatives ever meant. If you're like me, you didn't understand derivatives until you saw them enacted in physics. What I'm saying to you is a derivative is just the generalized idea of instantaneous velocity. It's a rate of change at a point rather than a rate of change between 2 points. And the way we understand a rate of change at a point is we say, oh, it's just a rate of change between 2 points. But we know that as the 2 points get closer and closer, our approximation, our average will get closer and closer to the truth. So we make those 2 points so close that they just surround our 1 point by an immeasurably tiny interval. That's what instantaneous velocity is. It is the first derivative of position with respect to time. It is the slope of the tangent line to a position time curve. That is it. We'll continue with this and we'll continue with sheet number 4 on whenever our next class is. I think it's Monday. You've been very patient. I'm going to hang out and answer any questions if there are any, but you can go. Thank you very much, all of you, and have a blessed, an electronic weekend. Okay, but we're good. Thank you. Goodbye. Yes, goodbye. Thank you. Okay, I'm changing the view. Have a great day. Yes, thank you. And also your dog, Kay. Have a great day.
Bye.
Bye. Thank you, Jada. Have a great day. That was Jada, I think. Thank you.
Yeah.
Okay. Have a great, and thank you for showing video, Sarah. Definitely, both of you. Okay, definitely type up, get points for showing video, seriously. And yes, oh, cool.
Hey, Professor.
Oh,
I had a question. I just want to make sure you're getting my homework. I wasn't sure